Real quick feedback, everything still sounds good on Zoom? Awesome, thank you. Mask on, and then just.
It's your call, because I spoke without a mask, so if you're more comfortable, you can take it off.
If you click,
Unless anybody has strong
if
objections.
he clicks that, if you click the arrow thing up top.
That's not the right talk. I don't know.
This is the right time.
No, that's Chris's talk.
Which one was it called? There you go.
Okay, so I can announce the talk.
You can announce and I'll just here to present those.
Just tell me when you're ready to go.
All set. No, you can only use the Lloyd laser pointer. That's what I'm saying is you have the arrow key for this. So just one of these guys.
Okay, go back to the title slide if you don't mind. Okay, so we're very happy to have Joseph Merovitz talk to us about the pion valence structure and the residual field model. Go ahead.
Hello, good afternoon. I'm Joseph Merovitz, and we're gonna basically talk about using the same model that Chris talked about, but using it on the pion. So let's do a little bit of historics. Experimental pions are difficult to probe because there's no free pions. You would need a pion beam, right? So we want to talk about the valence PDF of the pion at high X structure. So again, with the Brodsky-Farad counting rule, the X-weighted PDF at high X is 1 minus X to the beta V. So they found that beta V was 2 using PQCD models. And then Fermilab had Julian data for the pion with beta V equals 1.2 using leading order analysis. So this is basically the structure function for the pion. And you see that for high X, it's approaching 0. That is for this one. Next leading order analysis increased the beta V to 1.5 in 2005. And something interesting is that using resummation of soft gluons, the next leading log, the next leading order supported beta V equals 2. And you see this is not using, all the other ones are not using resummation methods. And this one, the red one, is using the resummation method. Okay, so recent development from JAM 18, which is Jefferson Lab Angular Momentum collaboration. They extracted the pion PDF through Julian and Sullivan process, which the Sullivan process there's like a virtual pion, right? And that's the exchange. And using Bayesian Monte Carlo method, and they get a beta V equals 1. So here's so this is the one we're looking at, the valence up, and very recently, 2021, they used the threshold resummation on Julian, which for different resummation methods, you get different beta V from 1 to 2.5. So depending on which method they use, they had different beta V. Okay. Okay. So I guess the Lattice QCD, they got the pion PDF through pseudo, and pseudo and quasi PDFs. And beta V depends on the method they use. So here they have different new, this is for new, and this is the basic structure you get for a PDF. There's some continuous function. This is for low X, this is for high X, and this is the weighted PDF that they have. And this is the spacing of the lattice. So Chris mostly talked about the model, but we want to use it for the pion. So he was talking about the nucleon had the soft contribution, no correlation, the 2-quark short-range correlation, and the 3-quark short-range correlations. For the pion, since there's just 2 valence parts, we're just doing the quark anti-quark short-range correlation. So here, the no quark correlation is responsible for the peak of the X-weighted distribution, is the bulk description, right? And then for higher X, then it falls down for the X-weighted distribution. I keep on forgetting. Okay. We're using Lightfront dynamics. What do we mean by the pion? Using charge symmetry, the valence PDF is the up valence of the pi plus equals the down valence of the pi minus. Yeah, so the charge symmetry. And so this is an expression that you can find in Kirchhoff. And here, this is for all X equals 1. This is for momentum, transverse momentum. And this is the wave functions. So the wave function could be split into the valence and the valence, which is the 2-quark, and then the valence residual system. And then you could basically the integral could be factorized into the X residual integral, the K-perp for both quarks, and the residual K-perp with the residual system. Relativistic. So for the quark, anti-quark, Lightfront wave function, we assume relativistic harmonic oscillator. Here we just set the quark masses equal to each other. So here we see like some kind of Gaussian for the wave function. This is a general expression, I think. And the K squared is just the momentum squared between the 2 quarks, the center of momentum squared with the Mandelstam S. And here, when we plug this in, and then the other wave function, the valence residual, we can also assume relativistic harmonic. There's we don't necessarily, the masses don't necessarily have to be the same, but and another method is let's see what happens if we have non-relativistic wave function like we did with the nucleon. So let's see, the pion is light, so maybe we don't need the non-relativistic. We just wanted to check, you know, fitting wise. You know? Yeah. So PDF calculation for the relativistic one, we get this one. And then for the non-relativistic one, we get this one. And then so we tried for the non-relativistic one, we use saddle point approximation. And we get this around, which is around this, which we get XB 1 minus XB minus 1, the residual mass or the pion mass. And here we get that the peak, we have 1/2, 1 minus the residual over 1 minus the pion. Where with the nucleon, we got 1/4, 1 minus the residual over the mass of the nucleon. So they're similar. This is so our work, we just started doing this like in November. So we're still working on it. And here's like some preliminary matches. For the peak matching, the advantage is that it's insensitive for high X structure. So this is for the soft contribution, doesn't affect much the high X structure. And then you got the chi-square minimization, which is pretty standard. And you compare it to the JAM 18 PDF. So here is the JAM 18. Here's our fit, JAM 18 our fit. Here's some of the parameters. This one's for the non-relativistic harmonic oscillator with the peak matching. This one's for the relativistic harmonic oscillator with the peak matching, and the relativistic harmonic oscillator with the chi-square minimization. The key takeaway is that you could get that the mass ratio between the residual and the pion, it's all around 0, which could mean that maybe the non-relativistic one doesn't make sense because the pion is so light. And then here are some of the Mellon moments. The first Mellon moment is the normalization. The second Mellon moment is the average X. And then we get all that the beta V is around 2. That's nice. So that was for the soft contribution. So now we consider a gluon exchange. This is combining the retarded gluon contribution and the advanced gluon contribution. Put them together. The light front is like a combination. And again, this is in X plus time ordering or light front time ordering. X plus goes this way. And so you look at it backwards. So this is for this part, and then this is the D1 is for this part, D2 is for this part. So basically the pion splits into valence residual, valence splits into the 2 valence quarks. Okay. Here's some of the calculation. Again, you've seen the wave function, using the light front rules. And, we get a hard kernel for the core-quark interaction. And this is what we're trying to calculate. And the amplitude simplifies, it's proportional to the hard contribution and the light front wave function. So this is like a factorization in some sense. Yeah, so that's our goal for this project. This is our side project. We want to do for the pion PDFs using the residual field model. For this one, we use the soft contribution or the mean field, and we model the light front wave function. And we get around, for high X, we get 1 minus X squared. And we're still working on the short range correlations. Thank you.
Right. We have questions. I have a two-part question on beta V. One is, do you have any reason why you think it should be 2 versus 1 or something in the other?
I think
just let me say the whole thing because then you can answer.
Yeah.
I'm so ignorant about this. What is it actually? What would that indicate about the physics one or the other? So if you can sort of squish those together.
So this is just for the one we got, this is just for the mean contribution, the soft contribution. So maybe we need higher contributions. maybe we get a different answer if you use the.
Is the beta V a PQCD prescription or PQCD prediction?
Yeah, Brodsky got using the constituent clamping rule. Basically, it's related to the amount of yeah, he gets this formula.
Is this related to, okay, so there's something I do know about, so I'll tell you.
It's a power on this.
Yeah.
So I know that if you take this limit in this Brodsky-Lepage stuff, you have a protein antiproton coming in, and gluon comes in, and you have to exchange another gluon to turn them both around. So the leading Fox state maps on the leading Fox state, and then this gives you a Q-square dependence that's predicted.
Yeah.
Now, is this something similar to that, where like it's basically assuming that the leading Fox state dominates the cross section? Is that the idea?
I don't think so.
I think that's.
It is, yeah, it's the leading phosphate.
Yeah, so-
Phosphates drop with higher powers. Here, IX, is usually the kind of really big, the X-ray. To the IX.
Okay, so yeah, that's what the underlying assumption is. The leading order process is your prion comes in, quark antiport dominates the scatter. It's not that it's the dominant part of the wave function, but it's the dominant part of the scatter. Because if you have a 3-quark or like 2 quarks and 2 interquarks, then you got to turn all 4 of those back to back in an exclusive process. Then that means they all have to exchange more gluons, which go like 1/2 Q². So if that's the picture, that what's dominating elastic scattering is the 2 quark components of the pion like. That's what it's.
And so is there any reason that, like, what does it tell us that physics wise in terms of 2 versus 1? Like, how does it actually? It seems like over the years, people fluctuate along this value.
So that PQCD argument is asymptotic.
Yeah.
You have to be in the infinite Q² limit. And so if you deviate from that, I think what it's telling you is that how far you have to go in Q² before that's a good argument. And I don't want to put words in you guys' mouth, because this is not mine, but that would go on US.
Yeah. Yeah, so this is not very, very high.
Yeah.
But they do the experiments at 3G. So they want to, so it's not obvious that the high Q² asymptotics is going to be the right answer. So it's sort of interesting to see whether that actually works, and does it work down to the Q² for the experiment.
Okay.
Any other questions?
So on slide 8, when you define FT, what is mostly involved the so you said that FT is
Yeah.
and I assume we can also use the charge conjugacy like that to the B bar.
For the
B bar in
Oh, yeah, of course.
you drive this company or is it-
yeah, I think so. This is so this is like what we mean by the pion valence PDF, because there's an anti-quark and a quark. So we want to have those charge symmetry for both. We don't want to just,
separate things PDF or B bar?
P bar or
Down, anti-down,
anti-down.
or do you just use the same pattern?
It would have to be different, right? Right. To use C quarks, right?
I think he's just saying that if you have a relationship between the U and the pi plus and the D and the pi minus, do you not have a relationship between the D bar and the pi plus and the U bar and the
the pipeline.
Yeah.
Is that what you're- Oh, yeah, yeah.
Yes, you do.
Yeah. 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 Sorry. I guess. I'll see.
Any questions on Zoom?
Oh, good job. Okay.
I got a comment. Regarding the ion period calculation allowance. I kind of comment on the student method that for the positive is based on dark moment effective theory. And the power company of dark moment effective theory breaks down as small x or large x. So the power company basically behaves like 1/x or 1/1 minus x. So if you want to use that to study large x and bigger, that's not going to be power company. It works well in the mid range, but not in the range where x is small.
So either side of X fails.
Yeah.
The power correction state there.
Okay, do we have any other questions? All right, so let's thank